Mars has captivated the interest of humanity ever since the bright red dot was noticed in the night sky. Hello, everyone. We are the 2023 SEAS Mars Exploration Team, and we present Drive Home, devising research initiatives for venturing and establishing a habitat on Mars for exploration.
Hi, my name is Quinn Brown, and I am a rising senior from California.
Hello, I'm Soren. I'm a rising junior from Los Angeles, California.
Hi, my name is Tina Lee, and I am a rising junior from Anahuac, Texas.
Hello, I'm Varsha Makkapati, and I'm a senior from Ellicott City, Maryland.
Hi, my name is Adithi Radhakrishnan, and I'm a rising senior from Raleigh, North Carolina.
Hello, my name is Aiden Schneider. I'm a rising senior from Reno, Nevada.
Throughout this 2-week internship, we've had the opportunity to work with Professor Adam Nokes from the University of Texas at Austin. His extensive knowledge and genuine passion for future space exploration continuously inspires us every day.
So why Mars? Mars shall be explored and inhabited for the Earth-wide realization of humankind's capabilities. This systematic exploration includes a scientific approach to experimentation in an adverse environment, creating a sustainable way of life, and emphasizing the search for life.
One of the most important steps in designing a Mars mission is determining where the mission will be located. There are several criteria that a potential site must meet, including flat, even terrain, a scientifically interesting environment, access to underground water ice, and preferably already available information about the site from previous missions. While any location on Mars would be an amazing opportunity, some locations stand out as superior. These include Acidalia Planitia, a large region once part of Mars's northern ocean, Arabia Terra, a volcanic area bordering on Acidalia, and Hellas Planitia, a large impact crater in the south that is the planet's lowest point. However, the location that we have chosen is Chryse Planitia, a large basin to the south of Acidalia Planitia. As you can see, the specific site of the outpost will be on the far eastern side of Chryse, just to the south of Aedes Fossae. Chryse Planitia is the perfect location for our Martian colony. The area's terrain is smooth and contains a manageable amount of rocks. It was once an ocean and contains volcanic debris and outflow channels such as Nicolaris Mensae, a few days' drive from the landing site, which makes it a region of significant scientific interest. It is located at the latitudes predicted to have ice at shallow depths, and the Pathfinder and Viking 1 landers which landed there gives us useful information about the region's conditions.
Mars Ascent and Descent vehicles serve as a gateway between the crew and the outside world. Minimizing MDAV weight is a priority, so we limit flights to less than 24 hours, prestage all habitat structures, and employ a 2-stage liquid propulsion system. To ensure a safe landing location across multiple missions, we utilize a binder regolith reinforced landing area and an anchored carbon fiber fabric barrier. This mitigates dust ejection and provides a level landing surface. Each module consists of an inflatable liner, a 3D printed radiation shield, and a geodesic truss-based shield. The inflatable liner is made of hydrogenated plastic and features 4 multi-gravity active mating adapters, maximizing the viable connections to other habitat elements. All 4 adapters can be flat-packed for space-efficient transportation. The liner offers both opaque protection and skylight-style windows. Its rounded top protects the inflatable from dust accumulation. Martian regolith is used for radiation shielding in the module's 3D printed cylindrical shield and tiles, fastened to its geodesic truss. During pre-staging, rovers position the liner, the Icon 3D printer prints the radiation shield, the liner inflates, and the triathlete robots assemble the geodesic truss structure, all autonomously. On arrival, the crew inspects the truss, guides the final tightening of the structures, and places regolith tiles into the trusses, adjusting liner pressure as needed for successful implementation. Modules are each designed to house 2 crew members. One science module is dedicated to a human research and biology lab, while geology and physics labs are housed in another. To isolate potential biohazards, one module is a dedicated medical area. One module would be dedicated makerspace to enable easy maintenance and isolate foreign object debris. The final science modules will house a system control center as well as a greenhouse. The same open source adapter is used for all module-to-module connections. We provide both short and long-distance pressurized commute options via double Stewart platforms and tunnels, increasing mobility efficiency across the habitat. Our adapter's utility ports transmit power, regulate pressure, and allow data transfer between modules. Retractable covers and hatches provide dust protection and thermoregulation. A key advantage of our habitation paradigm is that each module and its connections can be represented as a node and its edges, allowing us to optimize our habitat layout using graph theory. Our habitat is made up of two parts, a bipartite science section and a connected community section. Our habitat's layout's connected nature ensures module accessibility. The science section's bipartite nature ensures that there are no connections between high-risk laboratories, preventing a chain reaction of system failures from a single high-risk malfunction. The low-risk laboratories are similarly separated from one another, preventing cross-contamination between labs serving different purposes. An airlock junction connects the community section to low-risk laboratories. Not only does our graph theory approach ensure the safety and resilience of the first months of habitation, but it also is beneficial for habitat scaling. It allows Earth-based support crews to use graph theory to propose habitat expansions and reason about optimal layout and daily commute lengths using reachability and shortest path algorithms.
The power system proposed to generate energy for all aspects of the mission consists of three components: kilopower reactors, solar panels, and batteries. The fission surface power system units are inspired by the kilopower reactors under Stirling technology, also known as Krusty reactors developed by NASA, and will be used as a constant energy source for the settlement. The kilopower reactors are designed to follow a single converter to heat pipe architecture, which increases heat transfer efficiency and electrical power output for each converter. Another advantage of this design is that the modular system configuration actually allows each individual unit to be tested. Did you know that the Krusty reactors are also self-regulating, meaning they maintain constant temperature to accommodate all potential states of the power conversion system? If power demand rises, the power supplied will also rise so that the reactor can maintain its preferred temperature, or vice versa. The nuclear fission systems can even be scaled up to one-day power electric propulsion vehicles and the transport of heavy cargo to planets or other extraterrestrial locations further than Mars. Considering its many benefits, utilizing kilopower reactors is a monumental next step toward deep space exploration to Mars and beyond. The layout of the electric heat wires promotes an equal distribution of heat, therefore cold and hot spots within a room are prevented. The design is also out of sight for aesthetic and spacing purposes. Efficient planetary and interplanetary communication is vital to drive home, where our focus is to create a sustainable life on Mars and the transfer of new research and knowledge. The transmission period between Earth and Mars can take up a possible 44-minute communication round trip. To reduce the time allotted to the greatest extent, the Drive Home mission utilizes an optimal communication system to transmit laser signals that help secure data and transfer it at an extremely high speed. Compared to a traditional radio system, optical communication can transmit more data in a given unit with less power. More data means more discoveries. To achieve this, 3 pre-existing orbital relay satellites will be strategically placed 120 degrees apart, creating an optimal connection with a deep space network. This constellation eliminates conjunction as an issue because it allows for at least one satellite to be in line of sight with Earth at all times. Radio frequency communications can offer ground-to-ground transmission of information.
The next aspect of the mission is the food system. In the first phase of the mission, the journey to Mars, the astronauts will primarily rely on preserved food from Earth. Lyophilization, thermostabilization, and irradiation are 3 methods of food preservation currently used on missions to the ISS, and these methods can be further adapted for the flight to Mars. For Phase 2 of the mission, the crew's stay on Mars, a circular agricultural system will be implemented to provide astronauts with adequate fresh nutrition sources. A variety of plants including quinoa, turnips, and strawberries will be grown. The plants will be cultivated in a vertical tiered aeroponic system, which uses root misting irrigation to be water efficient. The plants are fertilized by misting water with dissolved compost from food waste and ash from incinerated organic solid waste. Inside the greenhouse, a complex network of light, temperature, and water sensors are used to regulate resource use. As part of the plant's natural cellular process, oxygen is emitted, which is captured through distillation for external use. In addition, plants emit ethylene gas, which speeds up the ripening process. To extend shelf life by slowing down ripening, the BioKez filter is used to break down ethylene into carbon dioxide and water. Once the plants produce yield, any excess food will be freeze-dried for future use. Also, the food waste from the greenhouse system will be composted and used for plant nutrition. Aside from the fresh food grown on Mars, astronauts need a source of meat for protein. Lab-grown meat solutions can be used for the ease of production. To implement this, animal stem cell lines will be preserved using cryogenic freezing and transported on the journey to Mars. Once the samples reach Mars, they will be thawed and grown with carbohydrates and amino acids for growth material. Overall, the use of preserved food, Mars-cultivated produce, and lab-grown meat provide astronauts with a palatable and nutritious diet focused on astronaut well-being.
There are plenty of opportunities for surface exploration on Mars. For geological research, the crew will go beyond the landing site to various regions to collect rock samples to be kept in a Class 10,000 lab. The samples will only come into contact with stainless steel tools, aluminum, and Teflon to prevent contamination, similar to how they are handled on Earth. As for biomedical research, the Drive Home crew will spend an unprecedented amount of time outside of Earth in gravity. They will regularly send health data back to scientists on Earth for analysis. The crew will also explore how Martian gravity affects the flow of intravenous medication and inhalable medication, such as albuterol in nebulizers. Studying impact on medical technology makes travel to Mars more accessible. Botanical research will be conducted based on the long-term yield and growth characteristics of Mars-grown produce. Camera monitoring can be used to determine the viability of farmings on Mars. For engineering research, the crew will study how convection is affected in Mars's gravity, as well as the impact of Mars's gravity on machinery and electronics. In the International Space Station, as pictured in the diagram below, a system of fans manually circulates the air to prevent carbon dioxide poisoning. The Drive Home habitat will establish a similar system, but research shall be done to develop alternate solutions. Previously, many plans included establishing separate sites for each new Martian mission. However, a single site allows surface mobility assets to be more concentrated, allowing for more efficient exploration. This design is also far more cost-effective. Furthermore, pressurized rovers, unlike unpressurized rovers, can better serve as tools in emergencies. They can also have a smaller design since the crew will not need bulky suits. Unpressurized rovers, however, have already been used in several missions, and since they aren't pressurized, they can be less costly. The triathlete has 6 limbs with wheels. The limbs can also lock to function as feet and traverse larger obstacles. The triathlete also addresses previous lunar roving challenges, such as improving wheel design to maintain flexibility and reduce forces of impact. Drive Home will use the Chariot, which addresses previous issues with the lunar roving vehicle. Its wheels can better resist the harsh lunar dust, and it will have 12 wheels to increase traction. Active chassis suspension will allow the astronauts to easily access the rover. The Chariot can recharge itself, function autonomously, and receive controls from astronauts in the vehicle, from the HAB, and from scientists on Earth, although there will be a time delay from scientists on Earth.
Most of the water the astronauts will use can be supplied using a highly efficient wastewater recycling system similar to that used on the International Space Station. However, the farm will require large quantities of water as well, and this will not be recyclable. Thus, we need a different way to get water. Fortunately, the solution lies just below the feet of our astronauts. Our landing zone in Chryse Planitia is at a latitude believed to contain sporadic water ice roughly 5 meters below the surface. This ice can be extracted using a Rodriguez well, where water shipped from the Earth is used to create superheated steam to melt ice underground. The new liquid water is either removed for use or recycled into the well to create more steam. This system will provide us with a surplus of water that will likely well exceed the amount the colony requires. The best option for obtaining oxygen is water electrolysis, using an electric current to separate the hydrogen and oxygen molecules, thereby allowing them both to be used independently. Water electrolysis also produces hydrogen as a byproduct which can be used as fuel. Oxygen is not the only problem, however. One of the main challenges with life support in space is not how much oxygen you have, it's how much CO2 you can remove. This would be done with disposable air filters, which would be replenished every 7 years alongside a new crew. These filters are small, cheap, and light, and therefore can be shipped in bulk.
Waste management. The waste management unit is an ECLIS system that is connected to the restrooms in our habitat. The unit is an incinerator that first removes urine through distillation, then reduces fecal matter to ash, creating safe, highly nitrogenous and phosphoric fertilizer for use in the greenhouse. Medical systems. Confronting life in an adverse and foreign atmosphere requires substantial planning to keep crews as healthy as possible. Health considerations for the crew include both physical and mental care, as well as preparedness for both planned and unplanned health impact. Planned health care includes activities such as exercise and checkup physicals, while unplanned care capabilities will be carefully deciphered through NASA lists of accepted medical conditions, or AMCLs. Physical health. Because the Martian atmosphere is still thinner than that of Earth, reduced pressure will exert less strain on the astronauts' muscles, causing slow muscular atrophy. While crew members will not have to exercise the 2.5 hours required in zero gravity, somewhere around 1.5 hours will be required to account for the 38% Martian gravity. Exercise can be derived both from daily crew work and from exercise equipment stored in the multi-purpose exercise module. To account for caloric intake, vitamin and mineral requirements, we have referred to the National Institutes of Health's Estimated Average Requirements Guide, based on a 2,000 to 2,500 calorie diet. Diets may also be adapted to consider high-risk environment factors, such as decreased gravity or higher radiation. We've defined water requirements for the crew to be between 74 and 101 fluid ounces daily. Radiation shielding in or on each member's person may be worn and woven into the suits that they wear, such as with hydrogenated boron nitride nanotubes. But shielding may also be taken orally or injected as medicine to the extent of our pharmaceutical capabilities. Mental health. The 7-year deep space round-trip mission requires tools to combat the several mental stressors. Spacious personal living quarters will provide privacy, while group activities will help fight loneliness and promote team cohesion. Finally, the crew will help care for life in the greenhouse, gardening to boost crew well-being and to provide a touch of home.
The timeline for the mission is as follows. In 2030, an SLS Block 2 launches the initial cargo and supplies, such as the rovers, 3D printers, and equipment. 200 days later, the cargo arrives, and, after Mission Control remotely confirms its functionality, the 3D printers begin assembling the HAB. A little over a year later, the HAB is completed, and after Mission Control confirms it is online, the crew is launched aboard another SLS. In another 200 days, the crew arrives and begins assembling the equipment, such as the Rodriguez well. Approximately 7 years later, the original crew departs, and a new one is launched aboard a third SLS. In conclusion, Drive Home offers a comprehensive approach to exploring the Red Planet. By using a human-centric design, we ensure the well-being of our astronauts. By using pressurized rovers and a carefully picked landing site, we provide abundant opportunities for scientific research. By extensively using ISRU, we ensure that our colony can be almost self-sustaining from day one. And by using a modular habitation system, we ensure that the mission can be expanded seamlessly. Humanity has been fascinated with Mars ever since we noticed that bright red dot in the sky. Drive Home provides us with the tools we need to reach up to that red dot and push towards new horizons.
A highlight of the program has definitely been the amazing resources and mentorship offered to us during the program. And we've also incredibly enjoyed the opportunity to learn more about the future of Mars exploration. On the other hand, a challenge our team faced was getting acquainted with all the domain-specific terminology without industry expertise. We also had to learn how to consider different constraints and requirements and combine a lot of different ideas to make one cohesive, comprehensive mission.
We are incredibly grateful for all the mentorship provided by Professor Nokes, Mr. Fritchie, Miss Miller, and Miss Baggio, as well as the rest of the SEAS team. Thank you for the opportunity to participate in the SEAS internship program and for all the funding, mentorship, and resources offered to us.
NASA SEAS has helped me understand just how tangible it is for me and others from backgrounds like mine to make meaningful contributions to the scientific community.
I wanted to expand my horizons in STEM by doing actual scientific research with NASA in the field of science that has fascinated me since I was little. SEAS was an incredible opportunity and an amazing experience, and I am truly thankful to have participated in it.
I wanted to connect with individuals my age who all desired to learn about the world around us and change it for the better. And I wanted to ask questions I would never have asked outside this program. I love how SEAS provided an opportunity like no other for me to interact with professionals who work in my dream field and foster an environment where I can contribute what I have to offer as a young, aspiring engineering student.
NASA SEAS encouraged me to consider space science more seriously as a potential career. I'm grateful for this experience as I was encouraged to ask questions and think about everything I learned in creative ways.
I'm extremely grateful for this opportunity. The NASA SEAS program has helped me apply my knowledge in space science and has inspired me to continue pushing to greater heights with my passion for space. Thank you.
The SEAS internship program has been the ideal environment for me to turn my passions into buildable skills in the company of like-minded peers and NASA professionals I've admired my entire life.
Drive Home strives to establish a sustainable human presence on Mars and pave the way for future habitat expansion.